So these are approximately similar or equal.
Yeah, I mean, I'm going to show this right now. It's our next topic.
Okay.
Okay. So we have a few minutes left. So my next topic is the relationship, between the p squared operator and L squared operator, okay? So what is the p squared operator? Can someone tell me?
Minus h squared, the Laplacian.
Very good. Okay. So on the other hand, what is L? L is Li, and it's epsilon I jk xjpk, right? If I don't use the Einstein convention, right? So then L squared then is Li, right? Or let me just use a different notation here, different index. So I'm gonna not use this, summation. So summation is implied by. So what is LL? LL is, we can write it as epsilon L jk xj pk, right? And the next L is epsilon L mn xm pn, right? Do you understand what I'm doing?
Yes, sir.
All right, so of course these are all dummy indices. J is a dummy, all of them are dummy indices, right? So the first index is L, and these indexes, I can call them different things. I have to call them different things, otherwise I'll make mistakes. They're, and indices which have the same name are summed over. Okay, so now let me rewrite this as epsilon L. Okay, now what I'm going to do is that I'm going to use an identity. So just notice that if I take epsilon L jk and epsilon L mn, there is a sum over L, right? But other than that, this expression is antisymmetric in J and K, right? And this expression is also antisymmetric in M and N. So, but the product is either 0 or 1. So I should be able to write this in terms of Kronecker delta. So all I have to do is to combine products of Kronecker delta such that I get the required antisymmetry. So I get delta delta minus delta delta. If I have J here and K here, and M here and N here, and J here and K here, N here and M here, then you can see that this combination is antisymmetric in J and K as well as M and N, and that this has either it is 1 or 0 or minus 1, right? So this is a very important identity that one uses a lot. So I'm going to use this here and expand this in terms of Kronecker deltas. So what do I get? I get L squared is equal to delta Jm delta Kn minus delta Jn delta Km. In other words, what I've done here, I've summed over L. Okay? So I've summed over L, and this is what I get. And then I have these other guys, the operators. And we have to be careful to keep the ordering of the operators. We cannot change the ordering, okay? Because we have to be careful. We have to use the commutation relationship whenever we change the ordering. And let's do the change in ordering now. So, but before that, so what are we going to do is that we are going to, in the first term, we are going to change the ordering of this thing. Okay? So if I do this, then I get delta J of M, delta of K of N. And then if I change the ordering, well, before, we have multiplying x of j and then x of m, p of k. We are using the commutator, and therefore we have to have minus I delta m k. So what I've used here is the fact that pk, commutator of pk and xm is minus I h bar delta km, okay? This is what I have used here. Okay, this is the first term. The second term, which has a minus sign, and then we have delta. Oh, I'm also forgetting Pn, so there should be a Pn over here. So this is in brackets. So this is what I've used. So let me erase this, otherwise it'll cause confusion. So we have P of n here, and then we have minus delta Jn delta Km, and then what we will do is we will exchange these two guys. So we have xj pk, and then we will have pn xm, but this was in opposite order to this, so there's going to be plus I delta. There's an h bar here that I forgot, nm h bar. Okay, is everything clear? I mean, the detail, the indices might be a little bit, I don't want you to be too caught up in that, but are you clear what I'm doing? The steps?
So can we do it differently? I mean, in the first, before the, how should I say? In the first term, can we use it for
Yeah,
xm and pn?
but, I'm trying to get it to be massaged in a particular form.
Oh, okay.
So that's why I'm doing this. I know where I want to get. So.
Oh,
Okay.
right.
So all you have to do is to just make sure that you agree with every step I'm doing.
Yeah.
Okay.
Mhm.
Essentially, I want to get x squared and p squared as much as possible. So now I can do the sum over the delta the Kronecker deltas. So in the first one, I will get there's a sum over j. So there's an xj here. That xj will become x of m. And there's an x of m here. See, I'm getting an x squared. And there's a sum over k, and that pk will become p of n. We have p of n. So here we have x squared, and we have here p squared. And then minus. Here, what we will have is something different. Here we will have minus I h bar. And then if you see, if you did j and m, so this would become x of m, and then and this k would become n, and this delta between these two will make sure that this x and this p, there's a dot product. So the second term becomes x dot p. Okay. So the second term becomes x. What about the third term? Well, again, we do both of those sums. then the third term becomes, we don't get x squared p squared because here we have xp px, but what we get is x of n yn, because if I do the j sum, j becomes n, and here we have x of j. And here, if I do the sum over k, it becomes m. So we get p of m. So we get xn pm and then pn xm. Okay, so not quite a dot product yet. And then minus, here what we should get is, again, we get minus I h bar x dot p. Okay? So we see that we get two factors of this thing. Two terms, sorry, not factors. So the first term we can write as x squared times p squared. And then we get minus 2 I h bar x dot p. And then here, what we have to do is that what we want to do is we want to commute. What do we want to commute? Yeah. So here
So
you
the
see.
p's commute with each other and
Exactly,
they.
exactly. So we can write this as minus xn pn p m xm. So we're almost there. All we have to do now is just commute this. Then it'll have the same form of this. So if I do this, then I have x squared p squared minus 2I h bar x dot p minus x dot p. The first thing is x dot p already. But here we get, if I commute these guys, I get x dot p, and then I will get a term which is, it was minus I h bar 3. Okay, why 3? Because there's a delta mm, and summing over m gives me 3. Okay, is that clear? So here we have a minus sign, so this minus will make it plus 3.
So this step wasn't clear to me. Could you
Yeah,
please
let me
explain?
break it up a little bit. So, what I'm doing is I'm taking this guy, PMXM, because this is a repeated index, there's a sum over this, right? So I can write this as XMPM minus IH bar delta MM. So delta MM is you're summing the diagonal elements of a 3x3 matrix. This is equal to, this guy is nothing but trace of I3.
Oh, okay.
Right? So that's why you get this 3. Okay? So if I do this, then I have x squared p squared. There's a plus 3 because of this minus sign, and there's a minus 2. So I get plus IH bar x dot p. And then from here, I get I think I'm missing a sign. I made a sign error somewhere, or yeah, there should be a there should be a plus sign here. Where am I? So yeah, over here, this came from, hang on. Okay, so I think it seems like there is some sign problem here. So I'm getting minus x dot p squared. Okay, but my notes show that there should be a plus sign. Okay, so anyway, I'll figure that out before the next lecture, but let's just stop here. So what have we derived? What we have derived is that L squared is equal to x squared p squared plus I h bar x dot p minus x dot p squared. Okay. So, and I'm not exactly sure of this sign, so I will be checking this sign. Okay.